Hello everyone, my name is Dr. Sunil Dahire. I am Associate Professor in Dada Ramchand Bakru Sindhu Mahavidyalaya, Nagpur. In previous section, we have discussed splitting of d orbitals in octahedral, tetrahedral and square planar complexes. So let us continue the topic. In previous section, we have discussed that when metal approach to ligand, when ligands approach to metal for the formation of complexes or coordination compound, interaction of d electrons of metal and ligand takes place, and because of that d orbitals of metal undergoes splitting. They divide. Splitting or division of d orbitals takes place. The energy difference between lower d and higher d is known as crystal field splitting energy. Crystal field splitting energy is denoted by 10 dq. Crystal field splitting energy, it is also denoted by 10 dq. In this section, first we will discuss the factors which affects on crystal field splitting energy. So let us see factors which affect crystal field splitting energy means 10 dq. So there are three factors which affect the value of crystal field splitting energy means 10 dq. First factor is nature of central metal ion, second factor is nature of ligand, and third factor is geometry of the complex. So let us see these factors one by one. First factor is nature of central metal ion. To crystal field splitting energy, it is directly proportional to charge on central metal ion. It means that as the charge on central metal ion increases, crystal field splitting energy also increases. Second thing is number of d electrons. Crystal field splitting energy is inversely proportional to number of d electrons. It means that as number of d electrons increases, crystal field splitting energy decreases. So there is inverse relation between crystal field splitting energy and number of d electrons. Third point is crystal field splitting energy is directly proportional to oxidation state of metal. It means that it increases with increase in oxidation state of metal. Fourth point is crystal field splitting energy, it is directly proportional to principal quantum number. Means it increases with increase in principal quantum number. So these are the points of central metal ion. So nature of central metal ion affects crystal field splitting energy. So let us see second factor, nature of ligand. So in this section, in this point, ligands are categorized or classified into two categories, weak ligand and strong ligand. Some ligand exert more crystal field or more field strength on the metal ion. Such ligands are said to be strong field ligand. On the other hand, some ligands exert less field strength on metal ion. Such ligands are known as weak field ligand. So, spectrochemical series. In spectrochemical series, the ligands are arranged in their increasing order of field strength. And when we compare strength of ligand with crystal field splitting energy, so crystal field splitting energy is directly proportional to strength of ligand. It means crystal field splitting energy or the value of 10 dq increases with increase in strength of ligand. This is the order of strength of ligand. Spectrochemical series gives the order of strength of ligand. In this order, we can see that I- is the weakest ligand and CO is the strongest ligand. So ammonia, ethylene diamine, Cn-, CO, these are the examples of strong ligand. In presence of strong ligand, crystal field splitting energy will be more. Third factor which affects the crystal field splitting energy is geometry of the complex. The geometry of the complex affect crystal field splitting energy. In square planar complexes, crystal field splitting energy is highest than octahedral complex and it is lowest in case of tetrahedral complexes. So there are two equations which gives exact relation between crystal field splitting energy in square planar complexes and delta O. So delta SP means crystal field splitting energy in square planar complexes is equal to 1.3 of delta O and delta T is equal to 0.45 into delta O. The order of these geometries are delta SP is greater than delta O and delta T. So these are the factors which affect the value of crystal field splitting energy or 10D. So let us move to the next point, John-Taylor effect. John-Taylor effect takes place when T2G or EG orbitals are unsymmetrically filled. So what do you mean by unsymmetrically filled? So if T2G orbitals contain 3 electrons, means in all 3 T2G orbitals there is 1 electron. So this T2G orbital is said to be symmetrically filled. If in EG orbital, if there are 2 electrons, it is said to be symmetrically filled. If in EG orbital there is 1 electron, it is said to be unsymmetrically filled. So let us take one example. In CuH2O6 2+ complex, it is the example of D9 system. It means in this complex, Cu2+ ion contain D9 electron and the configuration of this complex is T2G6 Eg3. In this complex, we can see that T2G is symmetrically filled, but Eg orbital is unsymmetrically filled. In Eg orbitals, there are only 3 electrons, therefore it is unsymmetrically filled. So John-Taylor effect takes place. John-Taylor effect takes place when Eg or T2G orbital is unsymmetrically filled. In this complex T2G, so there is only one possibility of electronic arrangement in case of T2G, but in EG orbitals, so there are 2 possible configurations. For EG orbitals, there are 2 possible configurations. First possible configuration is dx square minus y square has 2 electron and dz square has 1 electron. Means out of 2 orbital, one dx square minus y square has 2 electron and dz square has 1 electron. And second possible configuration is dz square orbital contain 2 electron and dx square minus y square contain 1 electron. So these are the 2 possible arrangements when EG orbital has 3 electrons. So let us discuss these 2 possible effect of these configuration on geometry of the complex. If the configuration of the complex is first one, in that case, in first configuration, as there is only 1 electron in d orbital, means as compared to x and y, number of electrons in z orbitals are less. Therefore, those orbitals which lie or those ligands which lie along z axis, they feel comparatively less repulsion. And because of that, so these ligands, they come closer to the metal ion. As the repulsion along z axis is less, so these two bonds along z axis get compressed. On the other hand, if the configuration is like this, in which dz square has 2 electrons, in that case, the ligands which lie along z axis, they will lie away from metal ion. They will lie away from metal ion. In second diagram, we can see that ligands, they are comparatively away from metal as compared to other ligands. So this is elongated geometry, and when we compare the stability of these two complexes or two geometries, it has been observed that second complex or second geometry is comparatively more stable. It means out of these two configurations, the correct electronic arrangement is second one. The same observed fact can be explained with the help of splitting and energy level diagram. So let us consider these are 5d orbitals in absence of ligand. In presence of ligand, first energy of these 5d orbitals increases, and later on these 5d orbitals divide into two parts. This process or phenomenon is known as splitting of d orbital. But after this splitting, these two EG orbitals, they are not equal in energy, because Z along Z axis interaction is less, therefore it is associated with lower energy. So two EG orbitals, they further divide into two parts, dz square and dx square minus y square. Similarly, out of 3 T2G orbital, 2 are associated with lower energy and 1 is associated with higher energy. Such type of further splitting of d orbital due to unsymmetrical splitting of T2G or EG orbital is known as John-Tiller effect. So this is all about John-Tiller effect. Again, in next section, we will continue the remaining crystal field theory. Thank you.